Hi, everyone. I'm going to talk today about innovations in physics education. Karplus is a book that was brought out in 1969 when I was at Berkeley and I was working with Bob Karplus. So I know a lot about what he's like and his style. I worked with him closely. He was a really wonderful mentor, a wonderful advisor. And I want to try to talk about what he put into this book, which has a lot to give to the current physics teachers. But it has a variety of things connected with physics reform, with teaching reform, some of which have been implemented and some of which have not been implemented. First of all, Karplus was the inventor of what's called the learning cycle, which is ubiquitous nowadays. I expect you've all heard of it. Initially, it was a sequence of 3 activities or 3 stages: exploration, invention, discovery. It's been elaborated and worked out in various ways, in various different guises and situations. But in essence, it's a cycle that the student goes through with the help of the teacher in learning, and it facilitates, helps the student, become familiar with the material and master it. And the key thing about it is that if you repeat it, if you use it repeatedly in various parts of the course, the student becomes familiar with it, and then they can start to use it themselves as a tool. And once they do that, they're really becoming an independent learner. They're really learning how science gets done. This is not all that different from what's known as the scientific method or the scientific methods. There's many different ways of approaching science, as I hope you know. But this does provide a really good starting point for the scientific approach. Now, Karplus used it in the book. He didn't do it, he wasn't as explicit about it as he might have been, but it certainly was used. And he was very explicit about it when he invented it, which was a good 15 years before he wrote this book. And he used it very explicitly and successfully in his elementary school curricula. He was the inventor and the leader of the science curriculum improvement study, an elementary school curriculum. The thing that was really new about this book was that he used the idea of modeling as a way of approaching learning of science. Now, modeling obviously has been used many times before. It's part of science. Scientists know what it is, but it really hadn't been put to use in science education. And there is a movement, an organization called the American Modeling Teachers Association, and modeling instruction is a trademark kind of thing. But Karplus's approach to it was much broader. It was much earlier, as he was the inventor of it. He saw it as a really fun, creative kind of activity that students could do relatively freely and relatively frequently, that it didn't have a lot of constraints on it. And his definition of it occurred via a bunch of very practical examples and through a classification scheme rather than some kind of abstract definition. And his classification scheme dealt with working models, analog models, and mathematical models. I'm not going to have time to go into this in real detail, but if you have a chance, his description of this is on the web, on the STEMteachersNYC website, and I can give you a reference to it so you can look at it if you'd like to. The next idea that I thought was important in his textbook, and I'm going to try to concentrate on the things that I think he introduced that have drawn attention, but that have not yet been implemented in the in full scale the way they should have been. And one of the key ideas there is interaction. Karplus saw this as a fundamental feature of the world. This was the idea that students could be introduced to at the very early age, kindergarten, if you will, certainly in elementary school, where things affect one another. And there's all sorts of examples socially and human interactions, but of course physically, interaction is a fundamental feature of the world. And the key thing about it is that if you want to define it physically, there have to be two objects. Interaction inherently is something that connects two objects together. It's a pair kind of phenomenon. The second kind of innovative approach that he used was energy as a unifying concept, and that it crossed physics, chemistry, and biology. And it was approached similarly in physics, chemistry, and biology. And I think if we look at it critically today, energy is approached in different ways in physics, in chemistry, and biology. Now, that doesn't make any problem for the individual disciplines, but it does make somewhat of a problem for the students because they have to think about it somewhat differently in each one of those fields. And in fact, if you look at it carefully, there's some serious conflicts that would be a good idea if we could approach it in the same way that Karplus did, so that students see it as one concept that stretches across all the fields. The other way he approached it, and again, this has been adopted nowadays, but again, not as much as I would like. And energy is often introduced as a type of energy, forms of energy, that we go about giving names to various types and forms of energy. And understanding represents being able to name the different types of energy when you see them. Well, there's a better way to do it. And the better way to do it is dynamically, in terms of energy transfer, in terms of the energy sources and energy receivers. That gives the students something to hang on to as far as processes in the physical world, as far as the way things really work, and not just trying to name things, because the names don't mean anything. It's the phenomena that we want to get to. The other thing he emphasized was that you look for observable changes. You look for how does the source and how does the receiver of energy change as the energy transfers occur. So if you have to use names for various kinds of energy, and sooner or later, I have to agree, you do have to use names for various kinds of energy, even if you're talking in terms of the dynamic transfer and the source and the receiver. The one thing that he really tried to stay away from, and that I really liked and really agree with, is to try to avoid the word potential energy or the term potential energy. This is confusing and ambiguous because to students, because potential seems to refer to something that could be energy. And when we say potential energy, of course, we aren't referring to that meaning of the word potential. We're referring to the fact that it can be mathematically captured in an equation for the potential, whether the gravitational potential, the electrical potential, or the magnetic potential, and that the derivative of that function gives you the energy. Well, for introductory students, you certainly don't want to get into that level of detail about what potential means. So Karplus's solution, and the one that I really like, is to stay away from the term of potential energy and to use the specifics. Talk about the gravitational field energy, electrical field energy, magnetic field energy, thermal energy, phase energy, or if you prefer the correct thermodynamic term, internal energy, radiant energy, electromagnetic energy. All of these kinds of terms refer directly to the process and to the way it's stored, the actual storage mechanism, so that it has a more of a physical basis, at least for elementary students. Obviously, when you get into the more advanced physics, of energy. Then you want to talk about the potential function, and you want to talk about potential energy, but that is for people that are at more advanced levels. And then once you've got the energy and the interaction concept established, you can develop the force concept as an outgrowth of those. That as objects interact, as they transfer energy while they're interacting, we can look at each of the objects that are interacting, and we can talk about what it is that's behind the changes that we see. And then you're dealing with an individual concept, something that you can name as a force. You can give lots of examples of forces so that students get an idea of the phenomena that you're dealing with. And then once you've got that established as a series of examples of the phenomena that are associated with the force concept, you can define it operationally with a spring balance. And you hang something from the spring balance, and you can determine the amount of force by looking at the deflection of the spring, or you can pull it to the side, which is probably a better way to do it because you don't have gravity involved. Now, important distinction here, of course, is to do it in an inertial frame. This will not hold. The operational definition of force in a spring balance does not hold in an accelerated frame. If you're in a car that's speeding up to the right, and you have a spring balance and an object that's hooked onto it, and you're accelerating to the right, you're going to see a force on the object, but that's not going to be the correct definition of the force. It has to be in an inertial, unaccelerated frame. And it is a bit of a subtlety, but it comes into play very importantly, of course, in circular motion. And that's one of the keys to understanding the difference between circular motion and linear motion, and understanding the idea of force, how the force is working in circular motion. Beyond this, once you're thinking about interaction, the force is the thing that acts on the individual object, but the really important concept to introduce is field, that you have interaction between two objects. And what is it that we can imagine to explain that interaction? The fact that it would occur magically through empty space is something that seems difficult to understand. So we imagine that there's a field, there's some kind of a extended influence that the two objects have on one another. This is something that is not impossible to deal with elementary students, with students that are studying physics for the first time. Force is a concept that does, in my experience, in Karplus's experience, did not come naturally to students. But the idea of field is a little bit closer to their intuition, that it's something that extends over a period of space, and that it can have an influence over objects that are in it, that you could have one object that exerts a field or that has a field around it, and that the other object is responding to that field, to that influence. So then, you have a gravitational field, and it can be constant near the surface of the Earth. That also could make it a little bit more understandable that the gravitational acceleration is constant near the surface of the Earth, that the gravitational field is constant. And then you can get into the idea that it varies with distance from the Earth. You have gravitational field maps, you have the electric field, you have electric field maps, you have a Coulomb force that's related to the electrical field, you have the magnetic field, and of course the Lorentz force connected with the magnetic field. Overall, the idea is phenomena first, then name. Start with the phenomena, get the students familiar with actual events, examples, without naming the concept that you want to get them to understand, and then either get them to name it, or when you do name it, it has a concrete meaning in terms of the examples that you've used. In terms of teaching specific topics, the ray and wave model of light is, is a really important topic. And the ray and the wave model can also be used to teach sound. So Karplus used it both ways, with light and with sound. So then the student got the idea that the ray or the particle model and the wave model were ideas that you could use more flexibly, that you weren't just tied to a particular type of phenomenon. Once you have that established, and you've taught the student about the idea of waves and how they behave, some of the concepts that apply to waves, you can develop the wave model of the hydrogen atom directly. You do not have to go through Newtonian mechanics. This was something that Karplus worked out in his book. Newtonian mechanics is at the back of the book, which was a revolutionary way of doing things, which I don't recommend you try, because almost nobody does this, and all the existing texts stick with starting off with Newtonian mechanics. Hi, I'm Fernand Brunschwig, and you just heard me talk about a lot of the ideas that Robert Karplus put forward. They were ideas that were incorporated in this book, Introductory Physics, by Bob Karplus, which came out in 1969, and which I revised in 2003, I think it was, and then again, much more recently, I prepared a second edition. If you're interested in this book and some of the kinds of things that I've been talking about, you can download it for free. It's available on the STEMteachersNYC website. That's STEMteachersNYC, that's all one word, .org/introductory-physics. And you'll see all the different chapters there. You can download. You can send me an email, and I can send you the password to the teacher's guide, which is not complete, but that covers 3 of the key chapters. So take a look. I hope you enjoy it. I hope you get some value out of it with your students, and let me know how you're doing and whether you found anything new to put in there. Good luck.